15th of March, 1943. Cold morning in Bethlehem, Pennsylvania. William Blalock stands in a converted warehouse, staring at a mountain of twisted steel. He is an industrial engineer, and he has a problem that could lose the war. The United States Army needs artillery shells, millions of them. Every month, American guns fire more rounds than factories can produce. Steel is rationed. Copper is scarce. New metal takes weeks to refine, ship, and forge. Meanwhile, across two oceans, soldiers wait. Blalock sees something others miss. Scrap metal sits in piles across America. Wrecked cars. Damaged tanks shipped back from North Africa. Battlefield debris collected and stored. All of it contains steel that was already refined, already processed. He asks a simple question. Why start from scratch when the metal already exists? The Army is skeptical. Scrap metal is contaminated. It contains oil, dirt, fragments of other materials. Artillery shells must be precise. A flaw in the casing means the shell explodes in the barrel, killing the gun crew. No one wants to bet soldiers' lives on recycled steel. Blalock requests one chance. He gets a contract for a pilot program. 30 days to prove his method works. If he fails, the project ends. If he succeeds, he might change how America fights. He starts with sorting. Workers separate steel by type. Tank armor goes in one pile, truck frames in another, shell casings in a third. Each type of steel has different properties. Mix them wrong, and the final product is weak. Blalock creates a classification system based on carbon content and hardness. Every piece of scrap gets tested and marked. Next comes cleaning. Traditional methods use chemical baths that take days. Blalock designs a mechanical process. Scrap passes through rotating drums lined with abrasive surfaces. The drums tumble the metal, scraping away rust, paint, and oil. Water jets rinse the pieces. The entire cleaning cycle takes 6 hours instead of 3 days. Then the crucial step, melting. Scrap metal contains impurities that weaken the final product. Blalock cannot eliminate them, so he controls them. He builds furnaces that reach higher temperatures than standard models. The extreme heat allows impurities to separate and float to the surface as slag. Workers skim off the contaminated layer. What remains is steel pure enough for military use. But melting creates another problem. Different types of scrap melt at different rates. If the furnace runs too hot, some steel burns. Too cool, and it does not fully liquefy. Blalock develops a layering technique. Dense steel goes in first. Lighter material follows. The furnace heats in stages, melting each layer at its optimal temperature. The process is slower than dumping everything in at once, but it produces consistent results. By mid-April, Blalock has his first batch of recycled steel. He pours it into molds for 105mm artillery shells. The Army sends inspectors. They measure the casings with calipers. They weigh each shell. They check for cracks using X-ray machines. They test-fire 20 shells at an artillery range in Maryland. 19 shells perform perfectly. One shell has a hairline fracture in the base. It does not explode, but the flaw is visible after firing. The inspectors write their report. Promising but not reliable enough for combat. Blalock studies the failed shell. The fracture occurred where two different types of steel met in the mold. The metals cooled at different rates, creating stress. He adjusts his sorting system. Now each batch uses only one type of scrap. The furnaces run separately for tank steel, truck steel, and shell casings. The batches never mix. He also changes the cooling process. Instead of air cooling the molds, he uses water baths with controlled temperatures. The shells cool evenly. Internal stress disappears. In early May, he produces a second test batch. This time, all 20 shells pass inspection. The Army places an order for 100,000 shells. Blalock has proven the concept works. Now he must prove it can scale. He needs more scrap. The Army begins shipping battlefield wreckage directly to his warehouse. Destroyed German tanks arrive from Tunisia. Knocked-out Italian vehicles come from Sicily. Each enemy tank that gets hit becomes raw material for American shells. The irony is not lost on Blalock's workers. They joke about sending German steel back to Germany, one shell at a time. But enemy scrap is not enough. Blalock contacts civilian scrap dealers across the Northeast. He offers premium prices for specific types of metal. Junkyards send truck frames. Railroads send worn-out rails. Demolition companies send steel beams from old buildings. Every week, trains arrive at the warehouse loaded with scrap. The volume creates a new problem: logistics. Scrap arrives faster than workers can sort it. Piles grow. The warehouse floor becomes a maze of metal. Blalock realizes he needs a system, not just a process. He designs a flow pattern. Trucks unload at the north end of the warehouse. Scrap moves through sorting stations arranged in a line. Each station handles one type of metal. Sorted scrap goes directly to the furnaces at the south end. Finished shells exit through a separate door to waiting rail cars. Nothing moves backward. Nothing sits idle. He also trains specialists. Instead of workers who do every job, he creates teams. One team sorts. Another cleans. A third operates furnaces. A fourth handles molds. Each team becomes expert at their task. Speed increases. Errors decrease. By July, the warehouse produces 15,000 shells per week. By September, 25,000. The Army wants more. Blalock is running 3 shifts, 24 hours a day. His furnaces never cool. His workers sleep in shifts in a building next door. Then he hits a new limit: furnace capacity. He can only melt so much steel at once. Building more furnaces takes months and requires materials he cannot get. He needs another solution. Blalock studies his furnace logs. He notices the furnaces spend 30% of their time heating up and cooling down between batches. That is wasted time. He develops a continuous feeding system. Instead of melting one batch, letting it pour, then starting over, he keeps the furnace at constant temperature. Workers add scrap at the top while molten steel pours from the bottom. The furnace never stops. Production increases by 40% without adding equipment. But continuous operation creates quality problems. Impurities build up in the molten steel. The slag layer grows thicker. After several hours, the steel quality drops. Blalock adds a circulation system. Pumps move the molten metal through filters that capture impurities. The steel stays clean. The furnace runs for days without stopping. By December 1943, Blalock's warehouse produces 40,000 shells per week. The Army asks him to document his methods. They want to replicate the system at other facilities. Blalock writes a manual. He includes diagrams, temperature charts, and timing sequences. He lists every mistake he made and how he fixed it. 3 more recycling plants open in early 1944, one in Ohio, one in Illinois, one in California. Each uses Blalock's system. Together, they produce more shells than traditional factories, using less new steel. The War Production Board calculates that recycling saves enough raw steel to build 6 destroyers. But Blalock sees another opportunity. His system works for artillery shells. Can it work for other ammunition? He experiments with mortar rounds, then anti-tank shells, then casings for naval guns. Each type requires adjustments. Mortar rounds need thinner walls. Naval shells need thicker bases. He modifies his molds and cooling systems. By spring 1944, his warehouse produces 7 different types of ammunition. The impact shows in Europe. After D-Day, American artillery fires an average of 30,000 shells per day. German factories cannot match that output. They face constant bombing raids and raw material shortages. Their production drops while American production climbs. The arithmetic of attrition shifts. For every German shell fired, American guns fire 3. Blalock's system also creates a feedback loop. American shells destroy German equipment. That equipment gets collected and shipped to recycling plants. It becomes new American shells. The cycle repeats. German tanks destroyed in France in June become shells fired at German positions in France in August. By the end of 1944, Blalock's original warehouse and the 3 additional plants have produced over 40 million shells. The cost per shell drops by 30% compared to traditional manufacturing. Production time falls from 6 weeks to 2.5 weeks. The military has more ammunition than it can ship to the front lines. Blalock receives the Medal for Merit in January 1945. The citation notes his contribution to the war effort, but he is already working on the next problem. The Army asks him to develop a recycling system for brass shell casings. Brass is even more scarce than steel. If he can recycle it efficiently, the savings will be enormous. He applies the same principles. Sort by type. Clean mechanically. Melt at controlled temperatures. Pour continuously. By March, he has a working system for brass, but the war in Europe ends in May. The Pacific War ends in August. The urgent need for ammunition disappears. After the war, Blalock returns to civilian engineering. He consults for steel companies and manufacturing firms. His recycling methods spread beyond ammunition. Factories use his sorting systems. Foundries adopt his continuous melting process. The techniques he developed under pressure become standard practice in peacetime industry. Blalock dies in 1967. His obituary in the New York Times mentions his war work in one paragraph. Most people never hear his name, but his impact remains visible. Modern recycling of industrial metals uses principles he pioneered. The idea that waste can become raw material, that the enemy's losses can become your supplies, that speed matters as much as quality. These concepts shape manufacturing to this day. The warehouse in Bethlehem closes in 1946. The furnaces go cold. The sorting stations are dismantled. The building becomes a storage facility, then a parking garage. Nothing marks what happened there. But for 2 years, that warehouse was a weapon as important as any gun. It turned scrap into shells faster than Germany could fire them. It proved that innovation in production matters as much as innovation in tactics. And it showed that one engineer, facing a mountain of twisted steel, could change the arithmetic of war.